So which one you prefer? You prefer that use the projector to project my handwriting on the screen or write on the whiteboard? Whiteboard is better?
Yes.
But I think the online student prefer to write on the projector. Whatever, doesn't matter. I mean, they don't complain, so I just assume they're okay with it. Oh, shh. Zoom in. Do we have somebody give me a marker pen? You have it? Okay.
If you do it on the projector, can you save the notes, like on web courses?
The what?
Like whatever you write, can you save that on web courses?
It's automatically record. Everything I write on the classroom, automatically record.
But as a document, you just pull up.
Exactly. If I use projector, projector shows up. If I use whiteboard, whiteboard shows up.
Okay.
Yeah. So it doesn't matter. I mean, it's just about the which way give you a better learning experience. But regarding the content, that's exactly the same. But I prefer to stand and give the talk that make me feel more active. But if I'm sitting here, I just falling asleep. You know what I'm saying? All right. So the this time we miss quite a lot of people. Anyway, so where did we stop last time? We were talking about the isothermal expansion, right? And the last time we stopped at the what? The iso. Can you be a theta one? Thank you. We were discussing the isothermal process. And versus the free expansion, correct? This is what we were talking about last time, right? And we were seeing that the okay. So the what we learned from last time is what? For the isothermal process, it looks like this, right? So we put in the heat reservoir, and then this one has a piston, and then we'll absorb some thermal energy or heat and do the external work, right? And for the free expansion, it's just like the sealed tank, and in the middle we have the separator, and we suddenly remove it with free expansion. Okay, we compare these two processes, and we find that there's one parameter, can be used, although the final state of the cylinders in both cases the same, right? Although the same, but if we will consider the reservoir, then we can find the parameter is the delta Q divided T can distinguish the process, right? For this process, the entire, if we consider that the Q absorbed by the cylinder and also the Q released by the reservoir, the total, change in this parameter equals 0. But for that one, for this one, delta Q times T is larger than 0, right? This is what we had last time. So then we know this parameter can help us to distinguish these two processes. Of course, I think most of people already know that we call this an entropy, okay? But anyway, so then there's the question. There's one question, okay? So we have no time to talk about that last time. We're talking about this one, sigma cube, right? Because this one do not absorb energy from the reservoir, right? But for the cylinder, we still have something. I mean, we still have something. It's like the delta S equals to what? It's equal to NR ln V final divided by T, right? And this one is equivalent to delta Q divided by T. Is equivalent to that one, right? Is equivalent to that one. Although they do not have thermal exchange. But from this one, it seems like usually temperature doesn't change in this system, and temperature doesn't change in this system either, right? So why we still need to have the T on the denominator? Not necessary, right? Whether it's possible for us just to simply calculate the delta Q to distinguish these two processes. Why we need to delta Q divided by T? Right? It seems like we can also calculate the exchange of the thermal energy and then distinguish this process. Okay, this one has thermal energy exchange, this one doesn't have thermal energy exchange. That's the difference, right? Again, this is, as I mentioned last time, this is just one specific example. We introduce this parameter, but I will give you another example that you will find that the delta Q doesn't work. Okay, the example is simpler. Okay? All right, so now let's consider you have two blocks, okay, two pieces of metal, copper, silver, gold, whatever, okay, but they are exactly the same, have the exactly same mass, okay, and then one piece is A, the other piece is B, okay, and this one has the temperature of T1, this one of TA, and this one have temperature of PB, okay, and at the beginning, that means the inertial state, TA larger than TB. Okay? Right now, we put them together. We put them together. Have the thermal contact, okay? What will happen? What will happen?
Even out.
Ah?
Even out in temperature.
Yeah. What's the final state?
Equilibrium.
Equilibrium. More precisely, what kind of parameter reach the equilibrium? Temperature. They reach the same temperature, right? So the final temperature definitely should be, okay, compare TA, TB, and final temperature. Where is the final temperature? Is larger than TA, smaller than TB, or something else?
In between.
In between, right? Something here, right? Right? This is final temperature. But anyway, so that's not a problem. So that means in the final state, we reach, this is final state, right? Or we can call it T final. Okay, so during the process, did these two blocks do any kind of the mechanical work to the external environment? Nothing, right? Because it's just a solid piece. Then what happened? What make make them reach the final equilibrium state with the same temperature? Heat exchange, right? Where's what the direction of the heat flow?
A to B.
A to B, right? A to B. Correct? Okay, so then in that case, from the A, we have what? Delta Q minus, right? Because they release some heat, right? We have negative. Correct? For the object A, right? At the beginning, we only consider a very tiny exchange, okay? But of course, the entire process, we need to do the integration. But we only think about at the very beginning, okay? Very small amount of heat change. And what about B? B will absorb some energy, right? And then delta Q times dB, divided by dB, correct? We sum them together. We have delta Q dB minus delta Q, right? So this term is larger than 0 or smaller than 0, or equal to 0. Greater than 0, right? All right, consider that second process. So we have a we have B. Okay, and they are at the beginning, they are at the same temperature. They have the same temperature, okay? And then we put them together. What's the final temperature?
T.
Still T, right? But when you put them together, can you guarantee that there's not a single peak, there's no a little amount of fluctuation, that they have a small amount of heat exchange at all? Maybe something happened, right? We cannot guarantee there's nothing happen, right? But anyway, so we just assume if there's some like fluctuation deviate from the equilibrium state or like the final state, then we still have a small amount of heat transfer from A to B, okay? So then for A, what about this parameter? It's T, right? What about for B? What about for B? Delta Q divided by what? By T, right? And the sum of them equals what? Equals 0. Correct, everybody? Equals 0. But you can see that for this kind of very simple, this kind of example is even simpler than that kind of isothermal process versus the free expansion process, correct? Very simple, just put two pieces together. And then they have some exchange, thermal exchange. But you can see, if we only consider the exchange of delta Q, then this one will definitely become 0, right? And for this one also equals 0. We cannot distinguish them anymore, right? So that means what? That means, although for the we can use the thermal exchange to distinguish the spontaneous free expansion process versus the reversible isothermal process, we cannot use that one to distinguish this kind of thermal exchange, correct? You know what I'm saying? But of course, we do not want to find a parameter. We do not want to find for each of the system a very specific parameter, correct? Okay, for this system, we want to use this one parameter. For the other one, we use another parameter. For the third one, we define something else. We want to find a universal parameter that applies to all systems. Correct, everybody? And that's the reason you can see, of course, this one probably works for both cases. Correct, everybody? You have a question?
Yeah, why is delta Q over TA negative?
Oh, because this one releases the heat. The
Okay,
heat
lost.
leave
Okay.
A. That's the reason it's negative, right? The same thing here, leave A. And inject into B, the B is positive. B gain something, A lose something. Okay. Okay. So, but still, we cannot generalize the definition of this parameter because I only talk about two cases, right? But how can we generalize, define this parameter to describe or to distinguish the reversible process and the spontaneous process? Okay, this is what we're going to answer for this class. But before that, any questions? If you have no question, I just assume everybody understands what I'm talking about.
I have a question. Why do we add these two?
Huh?
These two means Q divided by TA. We are adding these two
Yeah.
parameters.
Okay.
Why we are adding these two?
Why do we add A and B? Because you need to consider this one as A and B as a whole system, right? You have this system have two parts, right? You have to add them together. You know what I'm saying? Think about it. Yeah, you just need to. As a whole system. Okay. So that's the reason we add them together. Okay. Thermodynamics. Actually, the thermodynamics, the name is very misleading. You know? I'm going to explain why it's misleading. Hope that we have some time to discuss why the thermodynamics, this name is very misleading. Okay, so we're going to talk about next topic. The purpose, again, for this topic is to prove that delta Q divided by T is a universal parameter that can help us distinguish the spontaneous process and the reversible process. Okay? How to pronounce this word again?
Carnot.
Carnot. Carnot.
Isn't it French?
I think it's French. How to pronounce the T silent?
Yeah.
And what about no or no?
Carnot.
Carnot. Okay. Carnot. Okay, good. Good to know. Okay, let's talk about the Carnot cycle. Again, still remember that what's the name of the, what's the unit of the current? I mentioned this one, right?
Ampere.
How to pronounce it? It's a French, right?
Ampere.
Ampere. Oh, by the way, so do you know this one? If you know the quantum mechanics, do you know how to pronounce this one? Huh? Clearly? Schrodinger, right? Something like that. Yeah. Anyway. How to pronounce this? In the Spanish?
Near.
Nia, right? Okay, anyway. Okay. Don't waste my time. Okay, so actually, you know that I think for most of the students, for the first time, even myself, oh, by the way, the teacher who teach my thermodynamics is really bad. You don't know much about thermodynamics. Anyway, I hope that I can do a better job than my teacher. Anyway, so it's very abrupt, right? We were talking about we were about to introduce the concept of the entropy, right? But why we suddenly jump to the Carnot cycle, right? So the reason is, at the beginning, so this guy, Carnot, he was not trying to establish a parameter called entropy. Okay, he just accidentally find something. Okay, so the purpose why he built this kind of the Carnot cycle is he want to answer a question. So during that time, people already know the first law of thermodynamics, right? That heat can transfer to work and work can transfer to heat, right? And people already developed the heat engine, like your engine, your car is heat engine, okay? Combustion chamber. The question was, what's the largest efficiency we can achieve by a heat engine? Okay? Heat engine means what? Heat engine means we transform the heat into work. Correct, everybody? That's the heat engine. So but of course, from the experience, you boil the water and have the steamer engine to drive the train or whatever, and you release some heat vapor or whatever to the atmosphere. So we cannot 100% make full use of the thermal energy generated by the vapor gas or whatever to transform into the work. We always lose something, correct? We always lose something. So the question is, we define the efficiency of the heat engine in this way. Is that how much, or how many percentage of the heat engine transform into the work? Okay, this is a definition of the efficiency, right? But the question he wants to ask, at that moment people don't know. Okay, what's the highest? Can this one become approaching 100%? No one knows. People try their best to improve the engine. To have a higher efficiency. Who's work with that? Improve the efficiency of the steam engine. What's the name of the guy? What's the name? Who? Watt, right? He not invent the steam engine. He improved it. Okay. Just like the Thomas Edison, he's not invent the bulb, he improved it, okay? Anyway, but still not approaching 100%. What's the reason for that? And then, to answer that question, the Carnot, whatever, doesn't matter. I'm not French, okay? Very weird, right? So from this, to answer this question, he built up a cycle, okay? A build-up cycle. Why is a cycle? Because all the heat engine is a cycle, okay? What the cycle is that running again, and go back to the previous state, okay? But he wants to make the job as simple as possible, okay? Think about it. So we already discussed this one at the beginning of the class. So we have the ideal gas. Okay, ideal gas is the simplest one, right? We have the V, we have the P. If you can draw a curve, any kind of curve, on this PV diagram, that means this thermal process is a reversible process. Okay? But if you cannot draw the process on this chart, most of the case is irreversible. What's the reason for that? Think about it. Just give you a simple example, okay? Still the same thing. If we have an isothermal process, we know that the gas inside always have share the same pressure. Right? The pressure and the temperature of the gas is uniform anywhere inside the chamber. Correct, everybody? So we can use this P to describe the behavior of the entire volume of gas inside the tank. Correct, everybody? But the other thing is that think about free expansion process. We have the separator in the middle, and we suddenly remove it. Right? How can we describe the pressure of the gas inside the tank? There's no way, right? You gotta think about it. It's always the top, the molecules on the top escape faster than the bottom, right? So then the pressure drop down faster here than here. We do not have uniform pressure inside the tank, correct? And then because of motion, they also exchange energy. Although the final temperature doesn't change, but who knows why here is cooler than here or here is hotter than there? We don't know, right? Because of that, we cannot draw this process in the chart anymore because it's not uniform, correct? And because that's the reason this one, well, as we know, is also not reversible. It's irreversible process, right? And this one, you can reverse it, right? Got my point? All right, so in order to answer the question about the heat engine, think about it. At his time, he did not know much than us. Honestly speaking, think about it. If you were Carnot hundreds of years ago, what do you know? You just know what we talked for the last few weeks, right? The first law of thermodynamics is the conservation of the energy. We know there's some mysterious parameter called heat, but we do not know what it is, okay? We know the volume, we know the pressure, we can measure it precisely. That's good. Something else? No. If we already know the second law, this question doesn't exist anymore, right? But he knows something else. He also knows the ideal gas, right? PV equals nRT. That's the ideal gas, right? But you know the ideal gas, the model is very simple, right? The model of ideal gas is so simple. We do not have a lot of very interesting thermodynamic process in the ideal gas. So how many thermodynamic processes we have already discussed for the ideal gas? How many? You just name it. How many? Isothermal process? Something else?
Reversible.
Huh? Isothermal process? Something else?
Isobaric. Constant pressure.
Constant pressure, yes. Constant pressure. We do not call it iso what?
Baric. Isobaric.
I don't know that that terminology. But anyway, in the textbook it's called the constant pressure process, constant volume process. Something else? Adiabatic process. Something else?
Reversible.
Huh?
Reversible.
Something, right? More complicated, right? That's it, right? That's pretty much what we know, right? The current at his time, we can probably roughly say. Okay, so, but we know that if we have an engine and we can describe the circle inside the chart, the engine typically works in that way. You just go round and round, right? Pressure going up, volume going up, pressure going down, volume goes up. Let me see. Yeah, something like this, right? Yeah, on this, let me see. It looks really weird, but anyway. So something like this, okay? Something like this, okay? So the volume going down, pressure goes up, pressure going down, volume goes up. And of course, you have temperature also change, right? Temperature also change in this kind of cycle because remember, temperature is function of T and V, right? But it seems like we cannot calculate too much. This process is so random, right? We want to find something we can calculate, okay? But the thing is that we can form a loop. Okay, so right now we know what? We know several processes. So if you were Carnot, think about it. What do you know right now? You know the isothermal process? Okay, what's that? The P times V is a constant. Correct?
Yes.
So in the chart, it looks like this. Oh. Correct? And then every step, every point on this line share the same temperature. Okay, this is actual thermal column. Okay? And also adiabatic. So what's the PV relationship? Gamma equals to constant, right? Correct, everybody? Gamma is what? Gamma is the Cp divided by Cv, right? And how this one look? How this one looks like? This one looks like very similar to that one, right? But steeper, right? Because we have this the order here, right? To the order of gamma, so it's becomes steeper. Okay, so this is adiabatic line. And what's something else? Constant pressure process. Then P is a constant, right? It looks like straight line, right? And constant volume. V is a constant. Correct? So we just use this 4 types of curve or straight line to build up a cycle. Correct? To build up a cycle. Right? How many different kind of combinations? You can just combine them as one, in any kind of way you want to, right? You can combine, you can do this one process. You can have a constant pressure process. You can have a constant volume process and then link them with the adiabatic or the isothermal process. This one is a loop, right? Or you can make a constant pressure, constant volume, constant pressure, constant volume, right? And then, of course, you can also do this way, constant volume, constant pressure, and adiabatic, right? That also works, correct? But why Carnot do not select this kind of loops?
Less
Huh?
less efficient.
No. I will let you know they have exactly the same efficiency after we talk about Carnot. But I will prove it, okay? It's not because of less efficient. Some other ideas?
We focused on how machine works, taking heat and converting it to mechanical energy. We focused on that process.
Something else?
Is it to do with reversibility?
Huh?
Like, if it's reversible?
Everything is reversible. As long as I can draw the curve in the chart, everything is reversible. And the only reason is that the current cycle is the easiest one for us to calculate. Okay? This one is more complicated. We will do the calculation. Okay? No other reason, okay, it's just because the current cycle is the easiest one for us to calculate. Okay? Why do you, think about it. When you want to solve the problem, you do not want to artificially make it more complicated. You always want to simplify it, right? So but you can see the loop looks more complicated, right? No straight line at all. Everything is beauty. But why this one is easier? Let me explain to you why this one is easier. Think about it. When you're working on the heat engine, we always have the high temperature part, right? We drag the energy from the high temperature part, right? And then change it into the work, correct? And if we have the isothermal process, we know that all this curve will happen under constant temperature. The same thing to here. Everything here will happen on the constant temperature, correct? And on the adiabatic process, well, we want to calculate this one, right? We want to calculate this one. We definitely need to involve Q here, right? We definitely want to involve Q here. But for here, we know this is adiabatic, and for this process, delta Q is 0. We make the process simpler, right? Correct, everybody? And for this curve, the same thing, the delta Q here equals to 0. We only have the heat exchange on this curve and the heat exchange on this curve. correct? And let's go back to see this curve. Which I mean, you know, this part give the work, doing the work, right? This part do not do the work, correct? The volume doesn't change. It's doing the work, right? From this process, the constant pressure process, the gas is outputting or doing some work to the externals, correct? You think it's easier, right? The work is what? Is a PdV, right? And you just do the integration. Or eventually you have P times delta V. That's the work. No problem. But what about the heat? How much heat it take? It's more complicated, right? Because the volume expands, the temperature also change, right? Think about it. This is constant temperature line. The temperature constantly change, right? So we do not have a single heat source. We have multiple very tiny heat source, right? That makes the job more complicated, right? The same thing here. Although there's no work, the temperature keep changing. We have large amount of heat sources. That makes the entire job very complicated, right? But for this one, everything very simple. You only have a single two heat source, constant temperature, and for two processes, there's no heat exchange. Right? That's the reason why I kind of use that one, okay? I mean, yeah, I mean, the thing is like do not always think about this kind of big discovery is very mysterious, okay? So sometimes the reason behind it is very simple. They just lazy not want to do very complicated job. As simple as possible. Okay, so that's the reason the kernel select this one to study at the beginning. To use that one to study at the beginning. Okay. Before doing any kind of the more complicated calculation, let's first of all do some analysis. Okay. This is the Carnot cycle. The temperature here is T1. The temperature here is T2, right? And this one is the adiabatic process. This one is the adiabatic process. Correct? So we know that this is the isothermal process, right? And the pressure goes up, volume goes up, pressure going down, temperature keeps the constant, correct? And then we know that for this process we absorb some heat. Correct? Right? It's isothermal expansion. Isothermal expansion. Okay? The temperature the same. And this one, the piston going up. Output work. It's output work, so it take heat in. Correct? It needs to take the heat in. Right? The temperature doesn't change. Right? Temperature doesn't change means what? Means that the total internal energy doesn't change. Correct? Then the work is done equals to the heat is taken. Correct, everybody? Okay. And for this one, the same thing. This one is isothermal compressed process. Right? We just press it down. Correct? And then the volume going down, pressure goes up. But temperature goes up. Temperature keeps the same. Correct? And for this one, if you press the gas, what will happen? If you do some work to the gas, but the internal energy doesn't change, what will happen? It warm up, right? Think about it. I mean, you just have some piston, you push it down, then the gas got warm up, right? It's release the heat. Correct, everybody? And for this one, for this process, actually is release the heat. Correct? Is that correct, everybody? Any questions? I think we have some confusion face here. Any questions? I'll give you probably 1 minute for you to consider. If you have any question, let me know. How many of you have no questions? Raise your hand. So that means everybody have questions. What's the question? I mean, don't be shy. Let me know. Which part you feel difficult to understand?
Can you explain the isothermal compressed
Isothermal, you know the isothermal expansion, yeah? You know that the isothermal expansion process. Do you understand that one? Isothermal ion. So, what is isothermal mean? Iso means what? Equal. Thermal temperature. That means the process temperature is keep the same. Right? So we have a cylinder. We have a gas trapped inside it. Okay? And then it expands. Okay? And push the piston to go up. So, but we keep the temperature the same. We keep the temperature inside the tank the same, no matter how the volume and the pressure change. Okay? So if we push the piston up, how the volume change? Huh? How the volume change? Going up, right? How the pressure going works? Going down. What's the reason for that? Because for the ideal gas, PV equals to an RT. The T is constant, then PV is constant, right? V going up, P going down, right? But it's output some work. Because the work is defined by what? P times V dV, right? There's no that, we can put the negative sign here, doesn't matter. But you know that it's doing work to the external, right? Because it has some force, you push the piston up. Its work is like this, right? You do the integration, it's a work, the balance. Correct, everybody? So that's the reason when the volume goes up, the pressure although going down, but it's still doing some positive work to the externals. Correct, everybody? And we also mentioned that for the ideal gas, the total internal energy is only a function of T. Correct? It's only a function of T. The T doesn't change, the total internal energy doesn't change. Correct? And from the first law of thermodynamics, we know that the delta U equals to delta Q minus delta work. Correct? We give some energy out, we need to take some heat in. Correct? And this one, if the output is the work, you need to take some heat in. Correct? We can reverse the process. Right now, it's not isothermal expansion, it's the isothermal compression. We just push externally. We give some force to the cylinder, to the piston, to push it down. But we still keep the temperature the same. So in that case, how the volume go? We compress it, how the volume go? Going down, right? That's the definition of the compression, right? And then how the pressure go? Going up, right? The same reason, because PV and RT is constant, and V going down and P going up, right? Then, who is doing work? You doing work, or this cylinder is doing work? I'm doing work, right? Because I'm pushing it down, right? That means I'm doing some work to the cylinder. And because of this equation, the cylinder needs to release the heat, right? Got my point? That's the reason we have these two parts. But for these two curves, the delta Q equals 0 because this is adiabatic process. By definition, adiabatic means delta Q equals 0. Correct, everybody? Okay. So if we know that one, forget about this. Forget about the detailed process. Only from the conservation of the energy point of view, what is the work performed through this cycle? We don't need to consider how the volume change, don't worry about it. We only know that we input some Q. At the beginning of the cycle, we input some Q. And at the end of the cycle, we release some Q. Right? And from the conservation of the energy point of view, what is the work output by this engine?
Q plus.
Huh? No, it's not 0. Let me think another question. Okay? So I intake some gas and exhaust and release some gas. How many gas trapped in my body? It's just the intake minus the output, right? What about that one? You intake some heat, release some heat. how much of them transform into the work?
Q1 minus Q2.
Everybody agree with that? Because conservation of energy, right? Correct? That's it, right? And then what about the efficiency? Efficiency is delta W divided by Q1. Okay, we only care about the input. We don't care about the output, right? Because I mean, for the input, you have two outcomes. One is become the work. The other just got released back, released from the system, right? Only this one actually become the real work, and this one just wasted, correct? And the efficiency is just this part, right? And this one equals to 1 minus Q2, delta Q2. Correct? That's the efficiency. Is that correct, everyone?
When we're looking at work over heat, we're looking at how much work is being put in versus how much heat is being released.
We for the efficiency, we compare how much work got output by the system versus the total heat take into the system.
Also, heat is what drives the system. Okay.
Any question here? So that's the efficiency, right? That's the efficiency. Okay, so before we go to the calculate the specific value of it, we can, based on that, we can do some analysis. Okay. First of all, you know that just like I think about yourself or the kernel, and you have this kind of model. How do you know this engine has the best highest thermal energy? Highest thermal efficiency. How do you know? Oh, this one has high efficiency, that one has high efficiency, that one has high efficiency. I think there's one you were saying, right? The Canon cycle has high efficiency, right? But how do you know that? Why not this one? Why not one? Why not one? And why this one has the highest one? Because as I mentioned, we just randomly pick out one, which give us the simplest calculation process, right? But it's not necessary for this one the best model for the engine. It's so random. But how can we prove this one is the best engine, give us the highest efficiency? How can we prove it? How to prove it? Or what's your argument? Not necessarily mathematical proof, but what's the argument?
Curve length maybe. The curve length. Yeah, it is.
Curve length?
Yeah. So if we see the cycle, right? The delta Q1 and delta Q2. So if delta Q2 is higher, that means it's the work we are getting, right?
Yeah.
So if the work we are getting is higher, that means the efficiency is high.
Yeah, but how do you know the other part doesn't give you the even higher work? Think about it. What's the work output? Actually, the work output by the engine is the area of this kind of whatever it is. Right? For this one, the work is done by this one. How do you know? It seems like this one is smarter than that one. Right? Okay, let me show you the answer again. Don't spend too much time thinking about it. Okay, so if we want to prove something, we can either prove it directly or disprove the opposite. Correct? You understand what I'm saying? I mean, but it's not necessarily one way is better than one. But for that one, we can disprove that there's no other engine has high efficiency in this engine. Okay? How to prove it? Very simple. Let me tell you. So we know that we have two thermal sources, right? One is at T1, the other one as T2. Okay? And then we have this kind of very weird engine working between. Okay, we take some heat from the T1 and release the heat back to the T2, and then the difference become the output work. Correct? Right, everybody? And then if we have another type of engine has a higher efficiency, and no matter how weird the loop is, okay, probably the loop looks like something like this, it doesn't matter, okay? This kind of really weird loop, but it has a higher efficiency. Then what we can do is we make this output, we inject this output work to this engine with a higher efficiency. Okay? We put this work into this engine with a high efficiency. And then if this one, we reverse the process. Okay? We just reverse the process. For that one, we take the energy, we take the energy and do the work. But we can reverse process. We input some work and pump and then take some energy from P2 and release back to P1. Right? We can reverse the process. Correct, everybody? And for this one, the same thing. So we consider this process. We inject the work to another engine, and then this engine will take the Q2 from the T2 and release Q1 prime back to T1. Okay? You know what I'm saying? But the efficiency of this one is higher than this one. Right? Then what will happen?
That will be higher than this Q1, delta Q1.
Huh?
Delta Q1 prime will be higher than delta.
Exactly. Right? Then the delta Q1 prime will be higher than that one. Correct? Then what will happen? That means we just consider them as a whole piece. We do not want to see they have a very tiny engine inside. Then we spontaneously remove energy from one part of T1 to the other part. This kind of process spontaneously happen. Right? That means one part of T1 cooling down, and then the other part automatic warm up. Okay? So this is a ridiculous process, I mean, right? Understand what I'm saying? So that's the reason there's no way for us to find any kind of engine has a higher efficiency than the Carnot engine anymore. But actually, this is not accurate. The most accurate statement is any kind of this kind of loop has exactly the same thermal efficiency. Okay? As long as you can draw the loop on this kind of whiteboard, they have exactly the same thermal efficiency. Okay? What's the reason for that? Give you a more direct proof. Q. This is P, this one. Think about it. If we have a random thermal cycle loop, okay, a random loop, okay, we can always separate them, cut them to very tiny Carnot cycles. Right? We just cut them to very tiny Carnot cycles. Correct? And then we just combine together. And look at these two neighboring ones. So we have the Carnot cycle here. We have the Carnot cycle here. Right? They are neighboring to each other. And for that one, the cycle goes to this direction. And for this one, the cycle also goes to this direction. Correct? The cycle goes to this direction, the cycle goes to this direction as well. But on this one, for the up cycle, the process goes to this direction. And for the lower one, the cycle goes to this direction. They cancel each other. Right? And eventually, you only have this kind of envelope. Right? Because the contribution of all this tiny Carnot cycle just cancel each other. Right? But anyway, even if it's canceled, we can know that. That's the reason we don't need to worry too much about the shape. The efficiency always equal to this kind of Carnot thermal engine efficiency. Right? They're the same. So we don't need to worry too much about the shape of the circle anymore. Right? They always have the same efficiency. Got my points? Okay, the next question.
Like exactly the same or?
Exactly the same.
Exactly.
Exactly the same. Okay? Exactly the same. Okay, so the next question. We have two heat sources here, T1, T2. Right? And that's the reason we define, that's the reason we have this kind of expression. Oh, no, sorry. It's Q2, Q1. Correct? Right? So, is that possible for us without having this one? We only have a single heat source. The only reason why the efficiency cannot approach 100% is just because we're modeling the thermal engine, we introduce two heat sources. Correct, everybody? But why not a single one? Is that possible for us to build a circle with a single heat source? We know it's impossible, but why? From this figure, why is it impossible?
Where's the heat going to go?
No, yeah, I mean, why is that possible that we don't need the heat to go anywhere? We just want the heat all changes to the work. We only have one heat source and some engine working here, and change all the Q to the work. Is that possible?
Ideally.
Ideally, yes, of course. But whether it's possible or not. Ideally, we cannot say no, but eventually we know that you can change the 100% the heat energy into the work, only if the second heat source has absolute zero temperature, but it still need to be there, okay? But for the finite temperature, why we cannot, but the reason is that, the question is, why we must have the delta Q term to finish this kind of cycle? Why is it always be there? Although, I mean, it's fine. I mean, I can talk about that topic later. But why we have why we need to have delta Q here? Or we have to have another heat source, the T2 here. What's the reason for that? The reason is, you want to say something?
Something needs to be hotter than the other thing for anything to happen.
That's true. That's true. Exactly. But more strictly speaking. I don't, whatever. Okay, let me tell you the reason. So think about it. Engine is what? We need to finish the cycle, right? No matter how weird the loop is, it should be a loop, right? It should be a loop, correct? Think about it. If we have only thermal, we only have one heat source. We have what? We have this kind of isothermal process, right? Then then we have this kind of the adiabatic process. We have another adiabatic process. If we want to finish the circle without heat exchange, without any heat exchange, we must to have two isothermal, two adiabatic curve cross each other, right? In that case, we can finish the loop, right? If we only have one heat source, then this is isothermal process, and then we need to find two adiabatic process have the cross point. Correct, everybody? That's the only way we can finish this loop, correct? But we know that for the adiabatic process, we have this one, right? Constant, okay? And the constant is a function of temperature, correct, everybody? It's not function, I mean, forget about it. It's a constant, correct? If I fix the constant and fix a P, we only get a single value of V. Right? For different constant, we have different curves, right? If a constant equals 1, we have this curve. If a constant equals 2, we have this curve, and we have another curve. All this one, PV gamma equals to problem 1, PV gamma equals 2, PV gamma equals 3. Correct? We have this group of curves, right? But if this constant is fixed, and for a given point of P, we only have a single value of V, right? But if we want to have the cross, then for each of the P, for each of the P, we need to have a single value of V, right? But you can see that the constant is different, correct? You simply cannot find that solution. Got my point? Just try yourself to see whether you can do something like this. It's impossible.
So you're just saying they'll never intersect?
The statement is the adiabatic curve never cross each other. Right? Mathematically speaking, no. You just plot now. It never cross each other, right? They are not parallel, but they could not cross each other. Correct, everybody? Means what? I mean, you have the two constant, right? This is constant 1, this is constant 2, right? If you give a single p point, you definitely give two values of v. You cannot get a single value of v, right? Correct? You have 1 times v1 equals to 1, and 2 times v gamma equals to 2, okay? And the 1 times gamma v equals 1, 1 times v gamma 2 equals 2. Do you think v and the v1 and v2 have the same value? Definitely not, right? So never cross each other. In other words, we can never close this cycle with only a single heat source. In order to close it, we have to have another heat source, right? That's the reason this kind of the Carnot cycle answers two questions. One question is, what is the highest efficiency of the thermal engine? The other question is, why we cannot get energy from a single heat source? Okay, that's the reason why this kind of process is very important. Got my point? Any questions? Okay, this will appear on your final examination, okay? So if you don't really understand what I'm talking about, then you will be in big trouble. Anyway. All right. What happened? I heard somebody laughing. Okay, anyway, so let's go back to do some more specific calculation. To see is there any kind of more interesting conclusion we can get from this simple model. This is a P, this is a B. We know that we have the Q1 go to the system, we have the Q2 release back to the heat source. Okay, this is the Carnot process. And we know that the efficiency can be defined as eta minus Q2. Okay? And we know more than that. Actually, we know more than that. So we can calculate Q1 and Q2, right? For the isothermal process, we know that the delta Q equals to what? Equals to RT. V initial, V final. Correct? This is a conclusion we already calculated at the end of the chapter 1. Correct? Everybody knows this equation already, right? Okay, we give the name of each of the mod on this figure. This is state A, this is state B, this is state C, this is state D. Okay, it's go from A to B to B to C, C to D, and D back to A. That's the cycle. Okay, let's calculate the delta Q1 first. Delta Q1 in this process, right? Then equals to R T1 ln. What's the initial state? What's the initial state from A to B process? It's A, right? So it's VA divided by VB. Correct, everybody? And for that part, we don't care. It's an athletic process. There's no exchange of heat. Huh? Any question? Okay. And there's no thermal exchange. There's no thermal exchange. And this is from A to B. And from the B to C, delta Q, we know that equals to 0. So we don't consider this process. And then from C to D, delta Q2 is what? Is RT2 ln VC or VP. Correct? And because the volume So, and then from D to A, 0. Correct?
Does it go into counterclockwise?
It doesn't matter. It doesn't matter. It's counterclockwise. I mean, it's cycle, right? You can go counterclockwise or clockwise. Right? But right now we use the clockwise cycle. A to B, C to D, A, B, C, D, this cycle. But of course, you do the calculation from D back to A. The calculation is exactly the same.
But if you go clockwise, you input energy into.
You go to anti-clockwise, you input energy and pump the heat from Q2 to Q1.
Oh.
Right? That is your refrigerator. Right? You plug into the electricity, you take the heat from chamber to the environment. Right? If it run the opposite way, you give the heat, you're doing some work. Actually, if you want to check online, there are quite a lot of YouTubers doing the project. They find some the used refrigerator and take the compressor out and make some simple change and change it to the engine. Okay, it just reverses the cycle. Okay, it's just like the motor. You know that you have the electric motor, but if you rotate electric motor, you generate electricity. Okay, the entire process is reversible. You know what I'm saying? Yeah, the compressor. You have the compressor. Okay, compressor. I mean, use the refrigerator, and if you put fuel in, it becomes engine. Exactly the same thing. Check the YouTuber. There are a lot of videos on it, and you will know exactly the same. It's just about, as we will mention, it's going clockwise or counterclockwise. Okay. Okay. So where did I start? Anyway, so then for that equation, we will have eta. Oh, by the way, I think your pen is going to the end of it. This one equals to RT2 ln VC divided by VD and RT1 ln VA VB. Okay? But there's one thing we need to be very careful. And for this equation, we use, Q1 and Q2, we define all of them as positive, right? But for this calculation, you can see that for the Q1, actually this one is negative, right? Because for that one, we choose the gas as the object who receive or release the heat, right? But right for that one, we do not emphasize this definition. Understand what I'm saying? So there's something missing here. So actually, the Q1 should be equal to minus. Okay? Should be minus. You know what I'm saying? Because for this definition, we do not distinguish the direction of heat exchange. Yeah.
Is the volume change from A to B and D to C the same?
No, they are not the same. But we don't care. Well, I will prove that they are not the same. Okay. So we should have the negative sign here. Okay. We should have negative sign to make sure that all delta Q1 and delta Q2 are positive. Okay. We miss the negative sign. But anyway, so even negative sign, we just need to flip the order. Yeah. Okay. So this one equals to T2 minus T1, and then this is ln VC VD and ln VB VA. Is that correct, everyone? Is that right? But that's not the end of the story. That's not the end of the story. And you're right. We have no idea about the relationship between ABCD volume there yet, right? But you know that besides the isothermal process, we also know there's the adiabatic process, right? For the adiabatic process, we have this relationship. Right? And from that one, you will see that PB, VB, gamma equals to constant 1, and PD, no, we don't need to put constant 1. We know that this one has the share, then this one equals to PC, VC gamma, right? Because they share the same adiabatic curve. They have the same constant, right? So that one doesn't change. And the same thing here. The PA, VA gamma equals to PD, VD gamma. Is that correct? we make some change, okay? We know that PV equals nRT as well, correct? Then, for these two equations, we can transform into this way. For the first one, we just use one PV and one VB. Then what we have is VB gamma minus 1 TB equals to VC gamma minus 1 TC, right? We just replace one PB VB, replace with a T, correct? And the same thing here is the VA gamma minus 1 TA equals to VD gamma minus 1 TB. Is that correct, everybody? Something else we know? We also know TA equals to TB, right? TA equals to TB, correct? See that one? A and B, they are both equal to T1. And for C and D, the same thing. Both of them equals to T2. Correct? And we do some mathematical operation. So we can do I forgot the name. Anyway, so from these two equations, minus 1, T1. Yeah, we can divide this term by this term. Okay? I simply forgot the divide this term. Anyway. Then VB gamma 1 T1 divided by VA gamma 1 T minus 1 T1 should equals to VC minus 1 T2 and VD gamma minus 1 T2. Any argument? Everybody agree with me, right? Is that correct? Remove the order. Is that correct? Why? Okay. Right? Original can be transformed into that one, right? This number to be the same order, and that same, then the base should be the same, right? This is the base, this is the order, this should be the same. Correct? I think this answers your question. Right? Why the A and B the same? No, they're not the same, but their ratio is a constant. See that one? VC divided by VB equals to VB divided by VA. Then these two terms equal to each other. And the long one, I don't care. Okay? This term was removed. And then the efficiency is just the T1 minus divided by T2. Okay? In other words, we have the engine. We have the ideal engine. We have the ideal engine. If we only have two heat sources, if we have only two heat sources, we take some, this is engine, this is work. We take some heat from T1 and we release some heat back to the T2. Okay, we have the efficiency equal to that one. And the efficiency also equals to what? Is minus delta Q2, delta Q1. Correct, everybody? Then what do we have? If you consider these two expressions, we have T1, T2 equals to delta Q2, delta Q1. Okay? Or delta Q1 divided by T1 equals to delta Q2 equals T2. Right? So what's this one? What's this term called? Entropy, right? So you can see that Carnot cycle is kind of like, we already mentioned. So Carnot cycle is only one specific case for the reversible process, right? But it's only one example. And we also argue that all kinds of heat engine, as long as it's a reversible engine, they should have exactly the same efficiency. So in that case, any kind of thermodynamic process should follow this law. Okay? And this expression not only work for the isothermal process or for two parts contact to each other, but it's a universal expression that should apply to any kind of thermal process. Got my point? And we define ds equals to delta Q times T. Okay? And this one is entropy. This is not the end of the story, unfortunately, guys. This definition only works for this case. So what case it is? Reversible engine. It's a reversible engine. Okay? But what if the engine is not reversible? For example, like a car. The efficiency is definitely not that high, right? You can do some calculation. The efficiency might reach way lower than that one. So for most of the scenario, this equation does not stand. Okay? This is only for the ideal case. For the ideal case, we can define the entropy as a function of delta Q divided T. But for more general case, for the spontaneous process, this expression not correct. Okay? So why is not correct? Let me show you. Think about it. If we have the real case, this one should be smaller than the ideal case. Correct? We already know the ideal case gives us the highest efficiency. Correct? But for the real case, the efficiency must be lower. Right? Must be lower. So in that case, so the delta Q divided by T. Okay? For the ideal case, we still have this one, right? But for the real case, no, don't write in that way. We shouldn't write in that way. Let me see where we have a better way to express the equation. For the real case, we should have delta Q1 divided by T smaller than delta Q divided by T. Okay? This gives you a smaller efficiency. Right? We release more heat to the second heat source. This makes the efficiency lower than the ideal case. Correct? Is that true, everybody? For the ideal case, we know that the delta Q1, T1 equals to delta Q2, T2. Okay? This one is the ideal case.
So there's more entropy in an ideal case than there is in.
Let me answer that question immediately. So this is real case. Okay? Real case, ideal case. Right? Real case is smaller than one because you release more heat back to the heat source. This lower efficiency. Right? But for that one, it's equal. Correct, everybody? Everybody agree with me? Entropy. We know that entropy is a function of state. Right? The entropy is a function of state. It not depends on whether this process is reversible or not. Correct? As long as the engine go back to the original state, the entropy doesn't change. Correct? And we know that for that one, the entropy is what? The ds, right? Not the ds. We know that if you finish the cycle, then the entropy doesn't change. Right? The entropy doesn't change. Right? Because you finish the entropy from A to B to B to C to D and go back to A. The entropy doesn't change anymore after you finish the cycle, right? The same thing for this one. Because as I mentioned, entropy is a parameter, it's a thermodynamic process. It's a thermodynamic parameter. It doesn't depend on the specific loop. It's always, no matter what the shape is, it always go back to the A point. Then entropy also equals 0. Right? Then what will happen? You know that for the ideal case, you have this one equals to 0. But for the real case, you have this one smaller than 0. We need to sum. Okay? Yeah, we just put them all together. This one's smaller than the other one, larger than 0. And then, of course, what's the 0? 0 is the entropy, right? Okay? 0 is the change of entropy. So the more strict expression here is ds should be larger or equals to delta Q divided by T. Okay? The equal sign applies to the reversible process. And the otherwise, the change of entropy is larger than the delta Q divided by T. Okay? Other points? And this one, the equal sign only applies to the reversible process. But for non-reversible process, you have this one. Okay? Let me write down more specifically to consider the online student. Okay. So the relationship of the entropy and the delta Q divided by T looks like this. So for the reversible process, ds equals to delta Q divided by T. And for irreversible process, ds larger than delta Q divided by T. We combine these two expressions, the ds is equal or larger than delta Q divided by T. Other points? I think at the beginning I gave some hope, but right now I remove the hope. Why I'm saying that? Because from this equation, right now you think, oh, I really understand what's the definition of entropy right now. But then I told you it's not the case. Okay? So entropy can be larger than that one. So then here's the common question. What's the definition of entropy at all? We only know right now is from the reversible process, we can link the change of entropy to the exchange of heat. Correct? But what about for other processes? In reversible processes, how can we calculate the entropy? Right? So basically, that is about the definition or the physical explanation of entropy. That's the job we're going to do for the next chapter, the statistic. As I mentioned, entropy is something about statistic, right? It's not a mechanical parameter. You cannot find something in the Newton's mechanical picture about entropy. There's nothing there, right? But the origin of the entropy is a statistic behavior. Okay, we're going to talk about that one probably, I think next week. Okay, we're going to talk about what at all entropy is. Okay, but from the thermodynamic point of view, we need to remember entropy and the heat exchange have the following relationship. That guy have not pushed us to leave, right? Let me finish the talk. But for the reversible process, we already know the ds equals to delta Q divided by 1 by T, right? We can also change this one to delta Q equals to TdS. Correct? This one only works for the reversible process, okay? Remember at the beginning of class I mentioned delta Q is not the thermodynamic parameter. It's only a process parameter. The same to delta W. But we know how to calculate the delta W, right? We can express the delta W in terms of two thermodynamic parameters, pressure and volume. But after our analysis, right now we have one expression, at least for reversible process, for this parameter. We can express this kind of process parameter in terms of the thermodynamic parameter right now, correct? They're very similar to each other right now, right? And then go back to the first law of thermodynamics. We have du equals to what? Delta Q minus PdV, correct? And right now we can write it that way. Correct? This is the first thermodynamic equation you should remember. Okay, this is the first one. We have another 3 of them. Anyway, so any questions? Again, the equal sign only applies to the reversible process. And from that on, we have another more important conclusion. We give another definition of temperature. Temperature A can be defined in this way for the ideal gas. Okay? This is the new definition of the temperature. It's the variation of the total internal energy as a function of the entropy change. So that's the change of the energy. Okay? That's the definition of the temperature. Okay? There's quite a lot of very interesting phenomena there. Okay? Remember, I told you there's some professor working on the battery still don't understand why the battery has higher efficiency. All come from here. Okay? I'm going to talk about next time why this one very important. I will also introduce another very weird concept. It's called negative temperature. We know that the lowest temperature is absolute 0, right? 0 Kelvin. But there's a negative temperature. Go to YouTube to check some YouTuber. They can explain you what is negative temperature. Okay? Yeah, you can pick up. And